All right. Okay. Yeah, my name is Simon, and I'm excited today to tell you about some of the recent work we've been doing at Harvard in the Lucan group on different types of gate-based quantum simulations with our neutral atom arrays. So I think one kind of obvious class of models that would be interesting to realize on quantum devices are fermionic models, because they sort of underlie many different scientific fields, from chemistry to material science to high energy physics. And of course, they're known to be difficult to often tackle with our classical simulation methods. And this has given rise to a whole field of quantum simulation based on analog fermionic simulators. So the idea here is similar to what Monica described yesterday, is you can just put individual atoms, for example, fermionic atoms, in this two-dimensional optical lattice and just study their dynamics directly. And there's been tons of amazing results over the last 10 years, and recently now pushing to very low temperature regimes, as you'll probably hear from Marcus Greiner tomorrow. So I think digital approaches could offer some interesting new opportunities. For example, these digital devices are much more programmable, so we could start studying new types of models and new observables, and eventually we want to kind of reach very low error regimes with our fault-tolerant devices. But in practice, it can be quite challenging to encode fermionic statistics with qubit devices. And this is owing to the fact that qubits and fermions have different commutation relations. So the model that we started studying in the lab is called the Kitaev honeycomb model. And this is sort of a paradigmatic example of topological physics, where the interactions are highly anisotropic on this honeycomb lattice. So depending on the link that you're looking at, the direction of the link will either have XX, YY, or ZZ interactions, as shown here. And these interactions kind of leave certain operators conserved under the dynamics, in particular these 6-atom hexagon operators. And so we get kind of a rich phase diagram of different topological phases, depending on the kind of relative strength between these three terms. And in particular, when these three terms are sufficiently kind of equal to each other, we have this interesting non-abelian phase. And this sort of phase diagram has given rise to sort of a decades-long quest in materials science to actually try to engineer these anisotropic interactions in real materials. But kind of what's an interesting aspect of this model is that the way that Kitaev solved the model is by mapping this qubit system or the spin system to fermions. And the way this works kind of leverages the fact that these plaquette operators are conserved, and so you have sort of long-range entanglement across the system. And so the kind of Jordan-Wigner operators that you typically have when mapping fermions into qubits can actually become now local. So we have this, I think it's stuck. I don't know. I think the clicker is kind of stuck. Yeah, so the overall idea is that kind of using this long-range entanglement, you can actually turn this operator, which is typically really high weight in your qubit operators, and you can actually make it local. So the cool thing is sort of local fermionic operators, for example, nearest neighbor hopping, is typically these really high weight operators when mapping to qubits, but using this entanglement structure, we can actually make this now local in our qubit operators. Okay, cool. And this is kind of how it looks. So our kind of fermionic hopping now becomes local in our qubit interactions, which makes it much easier to realize in our kind of current quantum devices. And so this model is pretty interesting because it's this paradigmatic example of topological physics, but also shows how fermionic matter can be captured with qubit devices using this entanglement structure. So in our work, we're kind of going to probe both aspects of this model. So Misha discussed our platform yesterday, but just as a quick review, we're going to use reconfigurable atom arrays, where we have individual atoms trapped in these optical tweezers, which we can move around during the computation. And we store the qubit information in long-lived hyperfine qubits, which can last several seconds of coherence time. And then for our 2-qubit interactions, we just pulse a global laser, which excites the atoms to these highly excited Rydberg states for a few hundred nanoseconds and allows atoms which are positioned next to each other to interact. And we additionally have kind of single qubit addressing, so we can have universal quantum circuits within this platform. And some of the nice features that we'll exploit in these digital quantum simulations are the non-local connectivity that we naturally have by moving atoms around, as well as the ability to kind of implement interactions in parallel across the many qubits in our system. So how does this work in practice? So the way that we implement this Kitaev model is sort of in a digital way, where we can implement this first term of the Hamiltonian by moving the atoms along a certain link in this honeycomb lattice and changing the global basis into the X basis, and then applying a 2-qubit entangling gate between these pairs of atoms across the array. And then to implement the next term, we move the atoms again to a second location along a different link and apply a YY interaction. And finally can do this third link and apply a ZZ interaction. And by repeating this many times, we can sort of have this flocate implementation of this Kitaev honeycomb model. And kind of one of the nice features is that using these Rydberg entangling gates, we can actually at each time step have a controllable amount of evolution by implementing a controlled phase gate. So here there's kind of different gate profiles that we can use at each time step to control the amount of evolution. So the first step of our experiment is to initialize ourselves within this Kitaev honeycomb phase diagram. And the way we do this is creating a spin liquid state using mid-circuit measurement and feed forward. So we use these ancilla blue qubits and entangle them with our data qubits on this honeycomb lattice. We then move the ancilla qubits far away and locally image them, which projects these data qubits into a specific stabilizer state. Some of the ancilla readout values will just be -1. And based on these measurement values, what we do is we go in and with local single qubit gates, we fix the sign of all of the plaquettes, or all of these 6-atom loop operators across the system to be +1 valued. And so this is what our experimental data looks like. So here we have 104 qubits, or 72 data qubits on this kind of honeycomb lattice. And we verify that all the operators that we want are all finite expectation value. And actually using this kind of non-local connectivity in our system, we make this topological state actually on a cylinder, as is shown here, by sort of entangling the top ancilla qubits with the bottom row of data qubits. And we actually use this cylinder geometry to simplify a lot of our quantum simulations, and also allows us to do some additional error detection. So this actually initializes us on this top point of the phase diagram, where only one of the 3 terms, the ZZ term, is non-zero. And we'd like to now kind of use this structure of circuit where we move the atoms and apply interactions to actually drive the system, drive us into different points of this phase diagram. And in particular, we're pretty interested in this middle non-abelian phase. So we can apply a short, here, depth 6 circuit to actually reach any point in this phase diagram. And here we are probing this middle point, and we see that we have kind of a buildup of non-trivial, like non-local correlations within the system that actually match our theory predictions pretty well, especially as we add some amount of error detection. And using this data, actually, it's a very rich data set, which allows us to extract many things about the resulting state. For example, learn the parent Hamiltonian, and also extract the Chern number, which we see goes from a 0 value in this initial A phase to a value of 1 in this non-abelian phase, which shows that we actually have prepared this state in this non-abelian phase. And so I think these experiments kind of highlight that using this mid-circuit feed-forward plus some short numerically optimized circuits, we can actually start to target some interesting unexplored topological phases in this model. And this is sort of how it looks. So each individual green dot here is an individual atom. And the first part is we entangle these ancilla qubits with our data qubits, and we bring them far away and locally image them and apply these feed-forward pulses. And then we do this evolution, this Floquet evolution, where we're doing XX, YY, ZZ terms along different lengths. And this sort of long move brings the top row to the bottom to actually do interactions across the cylinder geometry. So I told you that kind of this model is also a way to map fermions into this qubit device. And so we also wanted to sort of explore how to encode and manipulate fermions in this fermion to qubit mapping. And so with our 72 qubits on this honeycomb lattice, it actually encodes 32 fermions on a square lattice. And one of the kind of characteristics of fermions is that when you exchange two of them, they pick up a -1 phase. And so we actually wanted to kind of show that the encoded fermions in the system would actually pick up a -1 phase when you exchange two of them. And to do this, we did a Ramsey phase measurement, so a Ramsey-style experiment, where you sort of compare the phase of two different basis states. So here, we start with kind of the system in a vacuum state where there's no fermions. And then using a sequence of gates, we can actually create a superposition of 0 and 2 fermions, as shown here. And then we can compare two different protocols, where each protocol is just a sequence of gates, which realizes some deterministic hopping across different lattice sites. And so we can compare the case where we fully exchange the two fermions, as shown in the bottom, to the case where we kind of hop the fermions to an adjacent site and hop them back, where the system shouldn't pick up a -1 phase. And we can do kind of a final sequence of gates to actually measure this phase directly. And we see this kind of difference between the two protocols as expected if our system kind of picks up this -1 phase upon fermion exchange. So this sort of directly verifies that we've sort of picked up, we've sort of realized these fermions with our qubit encoding. So now that we've kind of verified this fermionic encoding, we can actually try to start doing some initial experiments, sort of realizing different quantum simulations, fermionic quantum simulations within our qubit device. And sort of the encoded fermions in the system are naturally non-interacting, and there's kind of no notion of spin. But what we can actually do is we can split the system into two, and just in our head kind of label the left half spin up and the right half spin down to sort of be able to kind of implement an additional spin degree of freedom. And then what we do is we can have either sort of independent hopping of fermions within the two halves of the system, or using this long-range atomic motion, we can actually couple the two halves of the system by moving them on top of each other and applying kind of parallel entangling gates between pairs of qubits between these two halves. And sort of repeating this independent hopping and interactions, we can, again, have this kind of Flow-K implementation of a full Fermi-Hubbard model where you have both hopping terms and interaction terms. And so this is how it looks. So we have this independent hopping in the two halves, and then we bring the left half over and apply gates with the right half. And then we repeat this several times. So we can start the system in many different kind of initial states by just applying local qubit operations, which create kind of the right structure of fermions in this encoding. So here we created this checkerboard magnetization pattern where we have this kind of 16 sites here for our 32 total fermions. And then what we can do is we can apply these Flow-K cycles where we intersperse this independent hopping and these interactions and study how the staggered magnetization of this initial system evolves as we kind of tune the interaction strength. So here it's comparing in green is 0 interactions between the two halves, and red is with interactions. And we actually see that kind of with the interactions, you can have a suppressed transport of the spin degree of freedom that we added. And we can kind of tune this interaction strength by just changing the strength of the kind of gate that we are applying between the two halves and study this staggered magnetization as a result. So it's sort of a first step to showing that we can now actually extend these fermionic encodings to have sort of strongly interacting fermionic systems encoded with our qubits. So just to summarize, I told you about our approach to digital gate-based quantum simulations using this atomic motion with our atom arrays. And I showed you kind of how we use this platform to study different topological physics of Kitaev's honeycomb model, as well as starting to look into fermionic encodings. And I think there's many kind of interesting outlooks to consider. For example, extending these gate-based quantum simulations to other types of models, for example, in quantum chemistry, where I think this long-range qubit connectivity could actually be quite a powerful resource for these kind of near-term quantum simulations. And then thinking more into the future, along the lines of what Misha told you yesterday about our error correction work, I think it would be interesting to kind of study how we can co-design different types of quantum error correction codes, as well as use these deep error-corrected algorithms to kind of extend and encode these types of fermionic encodings. So with that, I'd like to thank the whole team. Here's the experimental team, and we had many great theory collaborators for this work. And thanks for listening.
Questions?